Hello, welcome advanced physics students. This screencast will be covering section 8.2 out of your textbook, that covering friction. So let's get a definition of friction and understand a cause of friction. Friction is defined as the resistance arising when an object moves through a medium or across a surface. And they're showing here a presumed microscopic view of the space between a chair leg and the floor. And the reason why we would have friction between these two is we would see some roughness here at the microscopic level, and actually the degree of roughness is what is going to account for friction. Now, if we were to look at a plot of force and velocity versus time, note that resistance to sliding an object is less than that to starting the object to slide. And what we are looking at is the difference between kinetic friction, which is sliding friction, and static friction. So I want you to imagine that you maybe have a big box, maybe in the middle of your hall, and it really is very, very heavy. So what you got to do is you've got to slide the box. Well, the amount of force that you're going to have to apply to that box to get it started moving, you're going to apply force over time. And when you maximize what's called the static friction, the box will then start sliding. And you'll actually see that if you could quantify this with a spring scale, you'd see the spring scale increasing in its reading of force. Then you'd see it drop right away, and you would see a constant force reading if you were pulling that box at a constant velocity. Okay, so again, we apply an increasing force for a while the box isn't moving yet, and the object does not move. But there comes a point when the object starts moving, and we see the force reading is actually less. So there are some laws to kinetic friction. The first law is, and we're looking at now kinetic friction. This is sliding friction, okay? Kinetic friction is independent of the areas of contact between the surfaces. So, and it applies primarily to hard surfaces. So you see a spring scale here that is pulling three bricks that are exactly the same mass, but they have them oriented differently. Well, believe it or not, it takes the same amount of force to pull these bricks along. Does not matter which way the bricks are facing. Pretty crazy stuff, huh? And this was actually pretty counterintuitive to me. In law number 2, kinetic friction is independent of velocity. And what that means, it's about the same amount of force that you're going to have to apply to overcome friction, whether the brick is pulled quickly or slowly across the surface. It does not matter. In law number 3, this is pretty intuitive actually. Kinetic friction along a horizontal surface is proportional to the weight of the moving object. As no big surprise, we look at the amount of force it would take to pull, and actually the force that you're pulling with this represents friction. It's a reflection of the amount of friction that you're having to overcome. Now I want to remind you that friction is a force and it opposes motion. So for one brick, you're going to have to apply so much force to overcome the friction and keep it sliding. If we add 2 bricks, it's a no-brainer. We see that it requires more force to pull those 2. And 3, of course, requires quite a bit more force. So a key factor affecting friction is the amount of force the 2 objects exert on one another. And as the object pushes down on the surface, imagine these bricks pushing down on the tabletop, the surface is pushing back up against the bricks. And we call that normal force. So there's a vertical force coming down on the tabletop that's moving downward, and there's a vertical force pushing back against the bricks. We call that the normal force. Normal forces always act perpendicularly to the surface. So as any given surface is tilted increasingly away from the horizontal, the normal force diminishes as a fraction of the object's weight. So this kind of makes sense. If you want to, think about how much easier it is to move your car down a slanted driveway than it is if you had to move that same car along a level road. So the reason why we see the force of friction being reduced as you see an increased incline is because the surface supports less of the object's weight. And when the surface is vertical, guess what? The object's in free fall. The normal force is 0. The object is in free fall, and the kinetic friction is also 0. Here's law 4. Generally, rough surfaces produce more friction than smooth surfaces do. So, in summary, the degree of kinetic friction felt between two surfaces depends upon the nature of the surfaces in contact. Now let's look at this idea of the coefficient of kinetic friction. So kinetic, or again, this is sliding friction, is proportional to the normal force, and we can show it like this. So sliding friction, kinetic friction, is directly proportional to the normal force. When the surface of an object when the surface an object is on is level, then the normal force equals the force of the object's weight. And we can express this something like this. As it's related to kinetic friction, we can express it like this. Oh, do you see that K there? That's a constant. So I will explain what that constant is. K is the constant of proportionality, or the coefficient of kinetic friction, or mu sub K. So we would rewrite this equation to look like this. The force of kinetic friction equals the coefficient of kinetic friction times the normal force of the object. And remember, the normal force is on a vertical surface is the same, on a horizontal surface is the same thing as the weight of the object. So just as a reminder, kinetic friction always acts against the motion of an object. If the kinetic friction is greater than the force moving the object will decelerate and come to a stop. So this means kinetic friction is greater. It's a tug of war on that object for forces. And if kinetic friction is greater, the wheel is going to quit rolling. To maintain motion, then, any applied force to a wheel, to a ball, or to a sliding object must be at least equal to the force presented to us by kinetic friction. So now imagine a 150-pound male sitting in a 30-pound chair. We're looking at 180 pounds total. And if the minimum force required to keep him sliding along the floor is 45 pounds, the kinetic friction then is also 45 pounds. And the coefficient of friction can be calculated. We would take the kinetic friction equals the coefficient of kinetic friction times the normal force, and we would rearrange that equation solving for the coefficient of kinetic friction, and that would be the friction force divided by the normal force of the man, and that would equal 0.25. So note that these units cancel themselves out, making this dimensionless. The coefficient of kinetic friction is dimensionless. So for any given system of surfaces, whether we're looking at a chair leg against the floor, or we're looking at a cardboard box against the floor, the coefficient of kinetic friction is approximately constant. It remains the same, although it may be affected by temperature as the particles on the two interacting surfaces are impacted. So we can imagine that if you have a surface that gets too hot, you're going to have some particle movement possibly on one of those surfaces. So that could impact friction. So the coefficient of kinetic friction varies greatly from one system to the next, hugely. Generally, the smoother the two contacting surfaces, the smaller the coefficient of kinetic friction. So for most surfaces, the coefficient of kinetic friction is less than 1. And what this tells us is that when an object moves over a horizontal surface, the kinetic friction, the amount of force that it takes to keep it sliding, is less than the amount of force it would take to lift it. It's less than the object's weight. So let's look at homework problem number 10. What minimum force is required to pull a 212 Newton sled at a constant velocity if the towing force is horizontal, directly horizontal, and the coefficient of kinetic friction is 0.23? So we would use this equation to solve for that, and we would use that equation in that form. And we would realize that in order to get this thing sliding at a constant velocity, it would take about 48.7 newtons. Now again, note that the sled is 212 newtons, and this value is less than 1. So now we're going to look at this thing called static friction. Static friction is the force you have to overcome when the object is sitting perfectly still and you got to get it moving. So static friction increases with applied force until the object suddenly begins to move. The very instant before motion begins, the value for static friction force is at a maximum. The coefficient of static friction, which is very similar to that for kinetic friction, it's mu sub s, is defined as, we would show it in this equation being used in this way. So we would calculate static friction. It equals the coefficient of static friction times the normal force of the object. So this equation looks very much like the last one we just used, where F sub SF is the maximum value of static friction. So although the coefficient of static friction is generally less than 1, for some combinations of metals, it is even greater. Now, I want you to take a look at these values. These are values that are probably experimentally derived. And this shows the coefficient of static friction. This shows the coefficient of kinetic friction. And note that if we look at how all these values here for kinetic friction are smaller than all of these values here. And that makes sense. These values here reflect what it takes to get a still object moving. And these values here show what it takes to keep the object moving once it has started at a constant velocity. So take a look at here, wood on wood. The coefficient of static friction is 0.62. Once we get it moving, note that it takes much less friction to keep it moving. Now take a look at these metals here. These coefficient of static frictions are all greater than 1. And what does that mean? It means it takes more force to actually slide these metals against one another than it does to lift them up. It requires more force to slide gold against gold than to actually lift the given sample of gold. Let's solve example problem 8.6. If a stage prop weighing 250 pounds must be pushed into position across a level surface, how much force is required to start it moving and to keep it moving? We are going to assume that the coefficient of static friction is 0.50 and the coefficient of kinetic friction is 0.30. So to solve the first case, we use this equation here, plug in our values, and we realize that the amount of force required to start it moving is 130 pounds of force. Recollect now that this is the maximum friction. Thus, if static friction is 130 pounds, the force to overcome it is also 130 pounds. If we solve for B now, we're asking how much force does it take to keep it moving once it started? And we use this equation that looks very much like the last one. That actually should be a small k there. I didn't change that character. I'm sorry about that. So F sub kf equals the coefficient of kinetic friction, times the mass of the box, or the weight of the box. And that is 75 pounds. So it takes quite a bit less force to keep the box moving. So how do we reduce friction? So starting to move an object or keeping it moving is easier if friction can be reduced. There are several ways that we can accomplish this. We can minimize the roughness of the two surfaces. We can choose suitable materials. We can use a lubricant. We can use rollers and bearings as well. So we can minimize roughness between two surfaces by sanding, smoothing, or polishing the surfaces in contact. And we can choose materials so their combination demonstrates a low coefficient of friction. If we're looking at using two materials and we see that they have a high coefficient of friction, well, we may want to look at different materials then to reduce friction. Lubricating leverages this principle that the friction between a solid and a liquid is typically less, except at high speeds, than the friction between two solids. So, definitely on motors, we use different types of lubricants and oils, lightweight machine oils, heavy machine oils. You want to make sure always, graphite is a lubricant. Always want to make sure you use the correct lubricant for the job. And rolling friction is less than kinetic friction. We know this, so we can use wheels, rollers, or balls to reduce friction even more. So that's all I have for this section. If you guys have any questions, send me an email, and I will see you guys in class.